Recording is on.
Okay, so we are recording.
We have WWJD here.
Welcome.
Nice to meet you.
Oh, nice to meet you.
Same.
So we were, well, let me figure out how to screen share. Hopefully that's going to work without issue here. Entire screen, allow. Okay. So we actually just started and are pretty early in the book here. And we were talking about local variables. We just got done talking about local variables having less indirection than other types of variables in Ruby. And then we went into some of the complexities that arose that are just considerations from the last book we read. And then now I think we're moving on to this snippet of code here. I did take a note that I do tend to use, and I guess I should hold off on my note because it was on page 51. So coming down here, we have this example where he's showing the time filter class. Mm-hmm. And here's the proc that it returns. So he is basically returning true or false based on whether the value is bounded by the start and finish. And then he's using nil, he's allowing nil he's kind of using nil for negative and positive infinity for time, like basically unbounded on the lower or upper bound. And in this example here, this start method is called twice and the finish method is called twice. So what he does here is that he cuts those calls in half by calling them once and putting them in the local variable. So now we're doing one method call, one attribute accessor call, and then two local variable calls. And he's mentioning that this is a performance improvement because the local variable calls are going to tend to be more performant than the attribute accessor calls. So that's what he's doing in this step here is he's calling self.start and self.finish once instead of calling them twice, and using a local variable to do that. The note I took for myself is I do this kind of thing pretty regularly to reduce the number of method calls, but I never do it for attribute accessors, and maybe I should give that some consideration. I mean, obviously attribute accessors are method calls, but I never really think of them as like an expensive enough method call to do this. And maybe it usually isn't. And he probably actually mentions that here somewhere that it might not matter for a typical use case. Then he's going to go further here. I'm trying to remember what he does here. Change. What's he doing here? Oh, so here he's pulling these out of the proc. So here, every single time this proc is called, we are fetching the start and finish. But since these never change over the lifetime of the time filter object, he can also hoist them out of the proc and only fetch them once, no matter how many times the proc that's returned is actually called. So it's just a further optimization.
So
basically
I have
reducing the number.
about that.
Go ahead.
I think,
yeah.
So I think this is the part where he talks about the proc being able to access the variable like just outside it.
Right.
Yeah. So that's kind of confused me. I don't know if you could explain a bit more about how that works.
Well, it's the closure thing that we talked about earlier, is that here I think this is a local variable to the proc, to its like scope or environment or whatever you want to call it. And then here, I think this is probably that use case where these get copied to the heap, actually. I mean, I'm not 100% sure about that, but this might be the case where when the parser, the like Ruby parser, and hopefully I'm not wrong about this, but I think that the Ruby parser sees that we are accessing start here and understands that it needs to copy it to the heap. And so this start reads that value from the heap, and so does this start. I believe that's the case. If it doesn't copy it to the heap, then there's going to be another environment pointer where this is here you're dealing with that environment pointer 0 back, and then this is dealing with it 1 environment back. I actually have no clue which it is. And I do know the new guy who just joined. I don't think he was here when we read the last book, but the last book went into a lot of detail about how this magic works in the Ruby runtime, either through environment pointers or through copying local variables to a proc. I think it was like called proc t or something like that. In a different location of memory that's independent of the stack, so that different things using the stack can all access these. So these things are on the stack. When this method is done, it's going to return this proc object, and we pop off the stack. So this stack frame is gone. But now something has a pointer to this proc object, and this proc object is referencing these variables, and we need those to survive. So I'm actually pretty sure this is that use case where Ruby understands it has to create a proc t object in the heap and copy this stuff to the heap so that it can actually be called from other stack frames. Pretty sure that that's correct. I mean, I'm not 100% sure. Is that how you're picturing it, Nelson?
It depends on whether or not you're saving the result of this proc object to a variable. I think it lives as long as the variable that you're assigning it to lives.
That's true. But I guess the thing is that when and who knows what kind of optimization it does, when the Ruby parser is going through here, it doesn't actually, I don't think it actually knows if the calling code is going to put a pointer to it or not. So I'm suspecting if you don't save it to a local variable, like if you don't save this proc object, I have a feeling it's copied to the heap and then is immediately available for garbage collection. But I'm not sure about that. I'm not 100% sure if that's how it works or not. But
that's how I would assume it works. Yeah, and
Okay.
just to clarify the first two assignments there, where you're saying start equals self.start. So if we remember the last book, when you do a variable lookup, you're looking at this basically this variable stack. What was the term for it?
Gosh, I mean, I think they referred to it as I think they were referring to it as an environment pointer in some
Yeah.
contexts. So it
So-
might be referred to as an environment.
Yeah, but
I'm not
whatever
sure.
the term is, the right term is. It was a pointer to an environment, the environment stack, and basically you just looked and saw what index of the stack to find that variable, versus self.start which is a method call. And when you have a method call, you have this thing called an R object. The R object points to its class. So you follow the pointer to its class. The class has a list of methods. So you got to search through that list of methods to see if that method is there. If it's not, it goes to its superclass and tries to find that method in the superclass. But that's a whole lot of other work involved in calling a method versus a variable, which is why there's a speed up here.
Yeah, was that? Sorry, I might have misunderstood the question. Was that more your question, Newton? Is that like what's this all about here specifically? Like why start and self.start?
No, actually, when it comes to this code, I understood until the point when he took the local variables outside the proc. But then what I was kind of trying to relate with whether now the explanation you've given me, I was trying to see whether it applies to what he talks about in the coming pages, where he says that some some keywords as scope gates, while others are not. So since we use def instead of define method, I was kind of relating it in that sense and trying to see whether that explanation applies side.
Yeah, it does. I think that actually it's the same concept. So something to keep in mind here is that this is see this array of times. Like, let's just pretend this has 100 times in it that we're filtering. If this has 100 times in it, then this code here is going to call the start method 100 times and the finish method 100 times. But here it's going to call the start method once and the finish method once. Does that make sense? And that's why this is actually, if there's 100 items in that array, this is a bigger speed up than this part was. Like this actually cuts down the calls a lot, right?
Yeah,
it goes from 100 calls to one call of each of these methods.
Yeah, because you call and then you store in the variable, and then you reference the variable you stored.
So here we have 200 calls to the start method and 200 calls to the finish method. Here we have 100 calls to the start method and 100 calls to the finish method. And here we have one call to the start method and one call to the finish method. So one cuts it in half and the other one takes it from wherever it is all the way down to one. Yeah. Okay. So then he comes down here and does this. And this is kind of cool. He basically, he's just there's like more optimizations he could do, but just going with the theme of the chapter. Here, because we are using nil to represent something as unbounded, and that's what this is doing. It's basically saying we're unbounded on the lower end, and this is basically saying we're unbounded on the upper end. So he comes down here and uses this information to basically say, if we're bounded on both ends, then I'm going to use a proc that bounds it on both ends. If we're only bounded on the start end, I'm only going to check the start end. If I'm only bounded on the finish end, I'm only going to bound on the finish end. And if we're completely unbounded, then I'm just always going to return true, because everything is part of nothing should be filtered out if we're completely unbounded. So this can give you a performance improvement, because now here in this situation, we're basically doing almost nothing. So basically he's skipping a bunch of computations based on what he knows about this. So basically he's kind of giving increasing techniques of improving the amount of stuff that the Ruby runtime is doing when you actually execute this code.
So when referencing this code, the very last code you were talking about, in my opinion, like when I was going through the book, I thought maybe he used the else if statements to cater to the various possibilities that this code is supposed to handle.
Mm-hmm.
And by doing that, he achieves the performance benefit as well.
Yeah, so the idea there being that these truthy checks here. So here you're doing two, like let's think of the worst possible case scenario is it's unbounded. So you're doing 1, 2, 3, 4 truthy checks. And by doing that, you're able to avoid two truthy checks and 2 comparison operators, or potentially 2 comparison operators. So basically the speed up is coming from the idea that these comparison operators are likely more expensive, which I actually don't know if that's true or not. But the point being, you have to keep in mind this proc is going to be called 100 times. So we're doing those 4 truthy checks once, and then for 100 times or potentially 1,000,000 times, we're actually skipping the comparison check. So like this unbounded case here, we're basically always returning true, whereas up here we have to do a truthy check 100 times and a truthy check 100 times. And in this case here, we have to do a truthy check 100 times plus a comparison 100 times and a truthy check 100 times plus a comparison 100 times. Does that make sense? It's hard to put into words, I think, but I think the understanding these optimizations revolves around the fact that whatever is inside this proc is going to get called 100 times or 1,000,000 times or whatever the case may be, whereas the stuff outside of the proc is only going to be called once. So calling as few comparison checks in the proc, this is basically calling as few checks as possible in the comparison procs themselves, because they're going to run many, many times. Does that make sense?
So when you look at all these 4 procs, which one could you say is the fastest? Because
this one would be the fastest.
Yeah, when the start and the finish are nil, right?
Yes, when start and finish are both nil, that would result in the unbounded case.
Yeah.
And like just thinking of the YARV code, I'm assuming this is just gonna push true on the stack and return. Whereas this has to call a comparison operator and put the result on the stack and then call return. So this is doing a comparison operation, which I think the runtime optimizes, but still this code doesn't even have to run the optimized comparison check.
Yeah, I think I get it now.
Yeah, I think the key to these is what I was showing up here. So this ampersand here, this is what's calling that toProc call. And it happens exactly once. So this toProc call happens once and it gets a proc object and passes it to partition. And partition is going to be ran once for every single member of this array. So we call toProc once, and then we call that proc potentially 100 or 1,000,000 times. So these methods return that proc. So the idea is the less you have in the proc, the faster the program will be, because it's the proc that's being ran 100 times. The code that builds the proc is only being ran once. This is only being ran once, but the guts of this proc is being ran potentially 1,000,000 times.
Mm-hmm.
Yeah.
I really do like his last example, and Ruby has made some syntax changes to allow for pattern matching in the language, and I think this would be a great example of pattern matching. And I put that in the chat. It's just like what the syntax would be.
Yeah, I'm just gonna go look real quick because I'm actually just curious. Oh, it's I don't see it in the chat. Oh, the chat of the tool we're using.
Yeah.
Well, I'll take a look later because I think I lost track of the tool. But I only discovered pattern matching like about a month ago, so I'm pretty new to it. I've only used it once so far in its write word assignment form, which I didn't know existed until like a month ago. But that's interesting. Yeah. Nelson, I'll go check that out once this call is over, because I'm actually curious to see how you would do it here. I'm assuming it uses the in keyword, right? But
yeah, the keyword is case and then in. So like
case and then in, yeah.
And then you give it an array of like the two elements,
start and finish. Yeah.
And then the keyword is true. The keyword is in, and then true and true.
Got it.
Yeah. It makes the different cases a little clearer, I think.
One thing that is cool about that approach that I read, and I guess we're off topic, but I think that if it doesn't find a matching case, it'll actually give you an error, whereas a normal case statement will just return nil and not do anything. So that could be useful in some contexts, just to make sure that you've accounted for every possible pattern match.
Yeah. Well,
Yeah.
the bane of my existence is trying to catch like nil errors.
Yeah.
And when you do, you're forced to do exhaustive pattern matching. It means like, oh no, you've accounted for all the cases, and you're not uh, unintentionally going to return a nil here.
Yeah, exhaustive is the word. So if that's your intent, but you get it wrong, you'll get a meaningful error message from the pattern matching. Yeah, so that's kind of cool. All right, so coming down here, this is something I never would have thought to do. So now we're doing the same concept, but with a constant. So again, the local variables have the least amount of indirection. He mentioned that earlier in the book, and working with that, he is hoisting the constant lookup of array. I've never once done this in my life. So I'll have to give this some thought, but he's, instead of doing the constant lookup every iteration, he's doing it once outside of the iterations. And I think he does mention somewhere here that he says you should only do this for very performance sensitive code, since the conceptual overhead of what you're making the code harder to read, and unless it's very performance sensitive code, it's probably not worth harming the readability of the code for a performance speed up that you're never going to notice. But this is interesting. Not only have I never done this before, I don't think I've ever seen this before in any code I've read. So that's a new technique that I've never seen. Yeah, so this is another one. This is the kind of thing I do this kind of performance improvement. So here we are converting the first command line argument from a string to a float, but we're doing it the number of times of the array. So if there's 1,000 things here, we're converting this thing to a float 1,000 times, barring any kind of runtime magic by Yarv or whatever. We're calling 2f 1,000 times, whereas here we're only calling it once. I do this kind of thing pretty regularly, but like I mentioned earlier, I've never done this before. So that was really interesting for me to see.
That performance improvement, not only does it seem like less readable, but it also seems like something that would be negated by a good JIT. Like once it goes through a JIT compiler, wouldn't that JIT compiler put in this speed up?
So I'm thinking it should be able to. It needs to invalidate some kind of cache or whatever if array is reassigned. So the downside there is that, like the Ruby constant, I think if you assign to this constant, you get a warning. But this code, so I guess the thing is that this code and this code actually don't do the same thing, because this is not actually a constant in a proper sense. Mm-hmm. But it's pretty aggressive to reassign the array constant, to say the least. That's a pretty dangerous thing to do. But regardless, it does seem like JIT should be able to handle it. And if somebody reassigns this constant, it would blow away some cache that would then, the next time you pass through this loop, it doesn't hit that precompiled code or optimized code, and has to actually either compile it again or run off the Yarv instructions. So yeah, it seems like it should be able to do it as long as it has a way to invalidate the cache if array is assigned to. That's something I think in most programming languages you can't do. I think in most programming languages, if you try to assign to a constant, you usually get a compile time error if it's a compiled language, or a runtime error. But I think in Ruby you get a warning, unless that has changed recently. But yeah. So down here, so just continuing here, he is changing the operation from a division to a multiplication. I'm guessing that multiplication is more performant than division, must be what's happening there. And then down here, he then hoists the multiplication So instead of doing the multiplication, so he goes from doing division 1,000 times to multiplication 1,000 times. He hoists that out to doing it only once. And actually multiplying by powers of 2, if the compiler is being smart or whatever, this is actually a really fast operation. But anyway, that's irrelevant. The point here being, we were multiplying 1,000 times, and now we are only multiplying once. So, yeah. I guess so. Go ahead,
Miles. You've kept on referencing the number 1,000. Where does it come from?
I'm just making it up. It's whatever the size of large array. It could be 100, 1,000, 1,000,000. I think the author is calling this large array because let's say this array is empty. If this array is empty, then actually this is more performant because it will do this 0 times, right? So that's why I think he calls this large array, because if this array is empty, it's going to do it 0 times. So this winds up being the best. If there's one object in the array, then whether you do this or this, it's going to do it once. And in fact, this needs to manage a local variable, whereas this does not. So it could actually be that even with one element, this is still better. So yeah, he's saying large array to communicate a large number. But since the author doesn't give, so I'm saying 1,000 or 100 or 1,000,000 Newton, because I think that was important to understand this optimization better, is understanding that this runs once. This that I've highlighted runs once. This runs 100 times or 1,000 times or 1,000,000 times. So the more that we can take out of here and relocate to here, the better. Does that make sense? So, and likewise, down here, if this actually is a large array, then the more we can take out of here and put outside of this large array dot reject call, then the more performant the code should be. So yeah, I made up the number.
Oh, I thought you had gotten it from the text. So all this time, I thought you had read the updated version of the book.
No. So coming back down here, let's see. So I guess I'll keep going unless there's other. I should check my notes because I might have had comments on this section. Let's see.
I just want to say thank you, Miles, for your in-depth note-taking and going over the resources.
Oh, sure. Yeah. Yeah, also thanks to Nelson, because he does a lot of research on the side as he reads these, in particular the last book. The last book was actually more out of date than this book, so Nelson was constantly telling us how things currently work. Okay, so yeah, I didn't have any notes on that. So here he's mentioning avoiding unsafe optimizations. This is stuff that I feel like should be obvious, but maybe it's not obvious. So here, do you remember what Nelson was talking about? If the runtime, like the JIT, optimizes this for you, it does have to have something in place to react to if this changes, if array changes. And if it has that, then great. Down here, we have an example where we're doing the optimization. And we had code where this might change while we're running it. In fact, yeah, this could very well change. At some point, if hash has a truthy value at the symbol A in its hash table, we should stop setting values to true. I actually found this snippet of code a little difficult to make sense of. But what we're basically doing here is we're basically taking a hash, and for every single thing that is in the large array, we're setting that value to true. And this kind of reminds me of how, if you remember in the last chapter, I think I don't remember if it was chapter 1 or chapter 2, but he mentioned that sets are actually implemented internally as hashes where the values are true. So it's almost like we're building a set, but he's kind of arbitrarily decided to stop building the set once we have A. It's almost like if the symbol A is in the set, then stop building the set is kind of what this code looks like it's doing. The problem here is that if we hoist this value out, we lose that behavior. We will basically do the right thing. We will do the right thing if the symbol A is already in the hash before we start processing the large array. But we'll do the wrong thing if that's not the case. And along the way, we run into the symbol A in the large array, because then we are supposed to stop building the set, but we're not going to stop. So he's basically giving an example of, I'm assuming you guys have heard that. So there's a joke about DNS, like the domain name system, or I don't know if S is system or service or what, where like there's jokes that like a hard thing in computer science is naming things, and another hard thing is cache busting or invalidating caches. So the joke is, I don't see what's so hard about DNS. It's just naming things in cache validation is the joke. But here we basically, it's like we're caching, but we're failing to invalidate the cache. Whereas up here, what Nelson was chatting about is YJIT could actually preemptively handle this for us, or some other aspect of YARV or who knows what could handle this for us. But whatever does this for us, it needs to be able to invalidate its cache in the event that we change the value of array. We're doing something sort of similar here, but we don't have there's nothing in this code that is going to invalidate this cached value here if hash changes. So this code gives the wrong behavior. He gives another example. I actually found this to be the same example. So he's using time.now, which changes over time as time moves into the future. I actually I personally, when I was reading this, I interpreted these both as the same problem. We have something here that can change over time. And then here we have something that not only can change over time, but will change over time. So to me, these kind of seem like the same problem. And by the way, I actually do this. I sometimes have to do this because sometimes I actually wind up in a lot of code where, for example, if I'm writing out some database records in a transaction and I want them all to have the same updated at and created at times as each other, like this is kind of the only way you're really going to do that, unless you use database triggers or something. And even that, I don't even know. It seems like that'd be even messier. So obviously, if you want to do this, then great, go for it. But if you're doing this for a performance reason, then it's a bad idea. And that seems like it should be obvious, but maybe it's not obvious. So I'll stop there. But I actually felt like this section was kind of obvious. Like this is like clearly a bug. So this optimization is clearly a bug to me, but maybe that's not obvious.
Yeah, I mean, it took a minute for me to try to understand that code as well.
Me too. This code, yeah. Once I understood it, though, that was the hard part for me. Once I wrapped my head around what it was doing, then I was like, oh, this is obviously a bug. But yeah, this was easier to I wonder if maybe a feedback to the author would be to start with this example, because this example is I think is much easier to wrap my head around. That if you have code that's sensitive to what time it is now, and you cache what time it is now, then you now have a stale. You have a stale cache bug right here. Like this is clearly a stale cache bug. If that's not what you want to do, but yeah. So I guess I'll keep going. This one was interesting, and again tied in with what we read in the last book. I had never heard of this term scope gate. So the way I would have thought about this before, so he basically shows there's no local variable called A, well, it's not defined, and then he assigns 1 to it, defining it. And then he opens up a new lexical scope with module. And you can open up lexical scope in other ways. And something he's pointing out here, and he's calling this type of opening a new lexical scope a scope gate, because the stuff outside doesn't carry over to the stuff inside, unlike with these blocks. So here in this block, now is outside, and then in here, now refers to this now out here through the block. So the big thing here is that blocks are closures, and module is not a closure. Module doesn't make a closure, but proc does. So he kind of demonstrates class, module, and def as these 3 scope gates, which again, I wasn't familiar with that term. And then he shows how it's different from define method, class.new, and module.new. So module.new, unlike module, will form a closure. So here he has A defined outside of creating the module, and then inside the proc for inside this closure that we're passing to module.new, we're checking if A is defined, and it is defined because we're inside a closure that contains the local variable that was defined out here. Now he's doing all of this to set up another form of optimization that I also have never done before. I've definitely used define method many times for meta programming, but I've never used define method for optimization. And he gives an example here where he computes basically a constant value. So here's the thing. You technically could change the first argument. It would be bad form to do it. But normally the first command line argument will always be the same. All of the command line arguments really should not change during the lifetime of the program. He's leveraging that knowledge to make an optimization where instead of doing a multiplication and converting a string to a floating point number every time we call multiplier, he's computing it one time and then leveraging that value through a closure every time the multiplier method is being called. So again, I've used define method many times while meta programming. It's never once even crossed my mind to use it as a performance booster. So I'm going to keep that in mind going forward. I'll probably try to bench if I find like a performance sensitive piece of code that I feel like I can apply this to. I'll probably attempt it and then benchmark it to see if it actually makes a difference or not. One thing I have done, by the way, is I have assigned this to a constant, not a local variable, and then use the constant inside a def. So he does point out somewhere in here that a constant, it operates through lexical scope as opposed through closures. So you can assign this to, if this was an all caps multiplier, you could use def and assign it to a constant, but he pointed out that constant lookups are slower than local variable lookups. So the choice for me, the choice for me in benchmarking this wouldn't be between this and this version. It would be between this version and the version where this is a constant and I'm using def. But this is fascinating. I never would have thought about that. So that was fascinating to me. So I'll pause there in case anyone had thoughts on this.
There's 2 years back, there was a presentation at RubyConf about speeding up constant lookup. And that's the problem with a lot of these performance things. It's like you have this little bit of esoteric knowledge that could or could not be true given what the Ruby authors have done. So I'm not sure if it's still the case that constant lookup is that slow, or if the changes they've done to constant lookup have made it much faster.
Yeah, so I think that's why I guess I would have to benchmark it. And if I didn't notice any noticeable speed up in the benchmark, I would just go back to the constant version, just because that's going to be more Ruby-esque.
The other thing is that that do there. So you're providing a block, and when you defined a module.new, you also provided a block, and it turns out that blocks get turned into procs, and that's the reason that you're creating a closure. It's because you're using a block.
Right.
So there's nothing special about like module.new, the function. It's because you're using a block and the block gets turned into a proc under the hood.
Yeah. True. Yeah. Cool. So if I continue down here, now he's talking about information hiding. So here he's using a constant to get instead of constructing, so he's using a constant to create a mutex to protect. I always wound up calling this a critical section. He's calling it non-thread safe code, which is more intuitive. So there's some non-thread safe code here. He wants to make sure only one. I actually wind up using monitor usually in Ruby, but I won't get into that. But there's use cases where this actually doesn't do what I want. But point being, we only want one thing to be executing this piece of code at any given time. So we're locking other pieces of code out of here while we're in here. He's storing that in a constant, and he's pointing out that users can actually just flat out access the mutex directly, which that might not be our intended public interface of the class. He uses private constant to make it private to discourage the behavior. And then he points out here that he's basically using that, and he's showing you can still get to it through this means. He says something here that I think is important and that I agree with and causes me not to worry about this personally. He says, in general, users that are accessing private constants deserve what they get. So I kind of feel this way. So I feel like if I've communicated my intent, I wind up not using private constants because I've ran into problems with them before, but I should try using them again because maybe they'll work the way I want now. But I wound up in some weird cases where they didn't quite do what I thought they were going to do. But regardless, if I've marked this constant as private and you're going to intentionally circumvent the public interface with constget, then I feel like I, as the author of that code, I don't have any responsibility to try to protect against that. Like, I'm fine with you attempting to do this. And if something goes wrong, it's because you've violated the public interface. Oftentimes, this means that you probably need to reach out and make like a feature request because there's probably some aspect of the library. There's probably some use case of the library that might be easy to add to it that I hadn't thought of or something. But anyway, he's pointing out that you can use a local variable in the closure to hide that data even further. So now he mentions that it is more difficult to get access to this mutex. That implies that maybe there is a way at runtime to actually access this mutex, but I don't know how to do it personally. But maybe there's some other esoteric set of reflection calls or something that'll let me get to this local variable. But regardless, by putting this in a local variable instead of a private const, he's making it even harder to access this private data. So, but yeah, to me, I think it's enough to communicate the public versus private interface to the end user. And then here, this could easily be, this could be an accident. In my opinion, this is absolutely not an accident. Like here, the user is clearly making a decision to bypass the public interface. So at least they know what they're doing here, whereas this could be an accident. So for me, that's why for me, private constant is good enough. Although something I should point out, by the way, is I think that the important takeaway here is just what is possible. This is, again, something I never would have thought to do. So, and I probably still wouldn't because I think it's enough to just communicate that it's private, but yeah.
So
yeah.
I have a question.
Yeah.
It's the very first time I'm seeing this mutex thing. I don't know what's the use case.
So he has this thing in here that says did the other person mention threads? So see this code, this block here, he says non-thread safe code. And actually mutexes will block the same thread. And that's one reason I don't like them. So here we have this method called in Ruby. So we have this method called safe here. If you call safe from down here, you'll actually cause a deadlock. And the reason is we come up here in the same thread, try to enter safe. We hit this mutex.synchronize, but because we are already inside of synchronize, we'll never release the lock and we get a deadlock. And so that's why I use monitor in a lot of these cases. But regardless, that's not the important part, I think, for your question. The important part is, yeah, it's just thread safety. And if you're not familiar, are you familiar with what it means to be thread safe, Newton?
I think it means preventing a thread from being changed or something along the lines.
Well, like let's say, like here's an example. Let's say that inside, let's say I update the user's first name in here, and I update the user's last name as two separate lines of code. Some other thread in the system could try to read the user's first and last name as a full name, and they might get the previous, they might get the new first name and the old last name. But maybe I don't want that. Maybe I only want them to either get the old first name and last name or the new first name and new last name, but not a mixture of the two. I'm just trying to come up with a random example. If I have if I use this mutex.synchronize in the method that mutates the first and last name, and I use the mutex.synchronize in the method that returns the full name, then they will never get an inconsistent view of the user's full name, because the code that you're not allowed to be inside the code that's mutating the first and last name and the code that constructs the full name at the same time, because this mutex.synchronize will block, it will wait. So you can kind of picture this piece of code as being like, you can kind of think of this mutex as just being a number, and there's like a concept called a semaphore, and you can think of a mutex as a semaphore of 1. That's again not useful at the moment, but just think of this as a Boolean flag. When we call mutex.synchronize, we check, is the flag true? If the flag is true, go to sleep for 1 second. When you wake up, check, is the flag true? If the flag is true, go to sleep for 1 second. Keep doing this until the flag is false. When the flag is finally false, then yield to this block. And when you're done, or sorry, once the flag is false, set the flag to true, yield this block, and then set the flag to false again. So basically, we have a flag that communicates to the outside world whether or not we are inside of this mutex. Mutex means mutually exclusive. So this is a piece of code that's mutually exclusive, which means if something is in here, everything else has to be excluded from it. Does that, I don't know if that makes sense, but basically you sometimes have operations that have to transition the data from a consistent state into an inconsistent state and finally back into a consistent state. And you might want to hide those inconsistent states. And sometimes these, have you heard of bugs that are called race conditions, Nelson? Or sorry, Newton?
No.
Okay, so there's a bug called a race condition, which this is something that can cause a race condition. If you didn't have these mutexes in the right spot, and you saw like, uh-oh, I got the user's new first name, but the user's old last name, someone could say, oh, there must be a race condition somewhere in the code. This is the kind of thing they're talking about. Does that make enough sense? It makes it so that only one thread of execution. So I always know the number of threads of execution that are inside, or that are executing code inside this block here is either 0 or 1. I guess that's technically not true, because you could violate it by like returning a proc out of here, which would be a really bad idea. But by and large, unless you're doing something where you're exposing the code in here to the outside world, either nothing is executing the code in here or exactly one thread is executing the code in here. I probably need to move on, but
yeah. There's in the, well, if we're moving on, then I won't say anything.
Oh yeah, you could continue. If you have a like a clarification or whatever, go for it.
In the bigger picture view of what's going on here, Ruby has this thing called a global interpreter lock, which means that only one thread of execution can happen at one time. But it does have this concept of threads, which means that you can have one thread going, and then for whatever reason, like maybe it needs to access the database and it sends out a request. Well, that request takes a really, really long time. So instead of waiting all that time, it'll just switch to another thread and say, okay, you can use the CPU right now. And when that thread is using the CPU, then it can start doing some work. And that's generally the way that it works in Ruby, is like you only have one single thread of execution, but you can switch threads at any one time. Generally, that's true. In JRuby, we saw that you can have two threads working at once, and when you have two threads working at once, they can. A lot of times, you have to be very, very careful about what variables they're updating, because if they update the same variable at the same time, then it could cause corruption in some way. So like the way I've heard it explained is a bank account. You and your wife share a bank account, right? You go to the bank, you have $100 in your bank account, and you say, I want $100. Your wife at the exact same time goes to the bank. She says, I want $100. And if you read the state of things at the exact same time, and you both say, oh yeah, I have $100 available to me, and you both get $100 at the same time, well, now your bank account is negative 100, because you got 100, your wife got 100, and all of a sudden you're negative 100 in your bank account. Oops, that should never happen. So that's why we use mutexes, to avoid those kinds of situations.
Yeah, you could also, another thing that happens with that is you could also wind up with 0. Like it could be that you both got 100 and the bank account went from 100 to 0 instead of negative 100, because it totally depends how the code's written, but if both threads go and say, how much money is in the bank account? And they both get the answer 100, and then they're like, okay, subtract 100 from that and update the bank balance with that amount. They're both at the same time going to do 100 minus 100, get 0. One will write 0, and then the other one will write 0, but it should have been negative 100. So all kinds of stuff can go really wrong depending on how the code is written.
Yeah.
That's a good example. That's a better example than the first name, last name. I like that example, Nelson. Or Newton, or sorry, Nelson. I wish your guys' names were different than each other, or were more different.
Well, it'll be up to you to give us nicknames.
Yeah. Oh, yeah. Okay, cool. So coming on down here, again, the more important thing, or at least the lesson here, and it's something I never even thought to do, and I would definitely, this is another thing I would benchmark for the reasons Nelson mentioned, which is that for all we know, right now, a constant lookup might be the same or better than looking up a local variable, and without debug, especially when we're doing a local variable across a closure. But anyway, so the next part was all around, was about naming local variables. I only took one note on this So this is a pretty big section. I basically agree with everything in here, except there's one thought I have personally, which is that depending on what level of abstraction I'm operating at, if I'm operating at a high level of abstraction, I'm more likely to use this kind of variable naming. And if I'm at more of a level of abstraction that feels like an implementation detail of what I'm doing, then I'm more likely to use a shorter variable name. So like, I don't know if there's an example in here. So here he has transaction processing system report, and instead he calls it TPS report. Depending on where I am, if I feel like I'm doing implementation, then I'm more likely to call it TPS report. But if I'm at at the public interface or extremely close to the public interface of the system, I might actually be more likely to use a variable name like this. Although this does look pretty bad here. So maybe that's not the greatest example, but yeah, that was the only thing in here that I didn't feel the same way about. But I have seen some people who just flat out ban single variable names like this. And I actually am totally fine with single variable names in contexts like this. This doesn't bother me. And I agree with his point where somewhere like in this here, when this happens, I'm less likely to use I. Although even here, I actually communicate some information because it's a very typical variable for an index. So I might not be the best example here. Oh wait, here he's using an example as type. He's making a different point. I'm sorry. Yeah. Anyway, what he was saying was basically, and I guess he doesn't give an example of it. If this block here were much more complicated, oh wait, this is a bad example. I'm sorry. He points out that here A is a bad usage, and I agree with him because array itself doesn't communicate anything, even though the method is so simple. Whereas here, if it were albums.each, yeah, up here. I'm sorry, guys. I was jumping around the book, but here he has albums.each and he's using A. I agree that a single character variable name in this case is totally fine. I do agree with him that here I would rather use album than A because this array isn't communicating enough about the code. It's not self-documenting enough, and using album instead of A helps self-document the code.
There is
Go
another option that's not listed here, and that's the keyword it. And it might be a better option here.
I've actually never used it. I've also never used, he uses this here. I've never used this either. Yeah, I haven't used this personally, and I haven't used it. What is it? Does it just refer to the first argument to the block?
Yeah.
Okay. That's pretty cool. I was aware that it existed, but I've never made use of it, literally. So, cool. He points out that K and V are useful, but then it would be confusing if you're nesting it, and so on and so forth. Okay. So he points out, and this is something we should have known from the last book, but if you have two variables that point to nil, then conceptually A and B both point to exactly the same object. But if you set A to an empty array literal and then B to an empty array literal, these actually reference two different objects. Just pointing that out there. Increasing performance with instance variables. Interestingly, I don't have any notes about this section either. I guess I must have felt like this was all pretty obvious stuff here. This is a type of memoization I've done many times. Yeah, I think that in this section here, I thought the things were obvious. He gives an example where like instance exec or instance eval are leveraged later on, but again, that's one of those things where if you're writing code like that, I feel like you kind of, well, let's see, that's pretty further down here. Yeah, I guess I should stop and ask if people had any thoughts about that. But I do take a note I actually took a note that, and maybe this is a different copy. Oh no, I actually took a note that I found it confusing that I was actually reading this in the paper book. I took a note that this spanning the pages actually kind of made it harder for me to understand quickly what the author was going for. So I could actually give the author that feedback, although I don't know how if other people experience that, but
Yeah, I have a question.
Yeah.
So it's about that part where he talks about the difference between nil, false, and how the immediate objects.
Yeah.
And is the implementation of these immediate objects in Ruby similar to the implementation of those same objects in maybe another language, or this is something that exists solely in Ruby? And why do I ask this? Like, to me, it seems like if you're designing a language, like, I don't know if when Max was writing Ruby, he planned it that, like, he had the concept in his mind that these immediate objects should be implemented differently compared to the rest of the objects in Ruby.
Yeah, I think for performance reasons, I think for performance reasons and historical reasons, probably most interpreted languages work this way or very similar to this way. So this is true, false, nil, and integers. And a lot of programming languages don't have a concept of symbols, but I think most programming languages that are dynamic languages and interpreted through a virtual machine, they're going to want to use a quote unquote immediate type or something similar. In Java, they call certain types primitive types. They're passed by value and instead of by reference, so on and so forth. They have different behavior for performance reasons and historic reasons. But yeah, I think I feel like Matt's had no real choice around these. I mean, he technically could have made it so that true wasn't an immediate object. It just would really hurt performance a lot. Like think about in particular integers. Like imagine adding 10 plus 10 and I have to go fetch the two values from memory, which so sometimes Nelson has talked about like this memory hierarchy where if you have something in a register, that's the fastest. Then something could be in like one type of cache. I forget which cache level these days is closer to the registers. Then there's usually L1. So then L1, L2, maybe L3 if the chip supports that. Eventually you wind up out in RAM, and then there's stuff on disk. And then there's stuff over the network. And I guess between disk and network, it can kind of depend on the technologies. But basically the point being, if like 10 and 11 are immediate values, I can put 10 and 11 in registers, add them, and get the result in a register. But if they're not immediate values, then hopefully they're in cache, because even if they're in cache, it's going to be much slower. But if they're not in cache, I actually have to go out to RAM, pull them into registers, perform the addition, and then write them back out to RAM. And that's much slower. And CP is something to keep in mind, is that most of the CPUs that these are designed, that these programs are designed to run on, they're highly optimized for working with these immediate values. Symbols you can think of as integers. So when the CPU is dealing with your Ruby symbols, it doesn't know the difference between a Ruby integer and a symbol. But point being, the CPU is much better at working with immediate values than non-immediate values. So if you can implement something as immediate value and get a good result, you're going to want to do that. And so I would imagine any serious programming language going all the way back to the dawn of time that is a dynamic interpreted programming language, is going to have this distinction between an immediate value and not immediate value. Now, I will say Ruby does its best to kind of let you treat these immediate values as if they weren't immediate values, but there's cases where it can't. So Ruby tries as best as it can to keep a conceptual consistency around these types, whether they're immediate or not, but it doesn't do it to the point where it has to severely damage itself performance-wise. I kind of rambled there, Newton, but hopefully that answers your question. That I would say that Matz basically had no choice. It's not like, if the question is, was this a killer idea that Matz came up with in the 90s? No, Matz already understood this concept. And in order to compete with the other existing languages, he basically had no choice but to do something similar.
So you've talked about how the implementation details of how immediate objects are accessed by Ruby. And from my understanding, are these the reasons as to why these immediate objects are faster compared to other objects?
So it's this here. So like if you read this line of text here, it basically, I think, answers the question you're asking. Instead of being a pointer that has to be dereferenced, meaning fetching something from RAM, they already have all the information you need. So yeah, I don't know if does that answer your question that you were just forming? They're much more performant for the memory hierarchy reasons that Nelson has mentioned in the past. The immediate objects operate at a more performance favorable level of the memory hierarchy than the non-immediate values. The non-immediate values give you a lot of flexibility and abstraction, but they operate at a different, less performant location in the memory hierarchy. So for example, if I want to compare whether A and B are equal, that's basically like one instruction. That's like practically, if they're already in registers, it's like one clock cycle. Whereas this is way more complicated, right? I have A is a pointer to somewhere in RAM, and B is a pointer to somewhere else in RAM. And I have to go access those, and I have to check, I have to probably it checks the size of these first. It's like, what's the size of this? Oh, it's 0, which means I need to pull that size into a register. What's the size of this? Oh, it's 0. Well, these two arrays both have a size of 0 as an optimization. Now I'll put true, which is an immediate value, into a register. So that's putting true into a register is fast. But does that make sense? This is so this here is like asking, is 0 equal to 0? This is similar to just saying, is 0 equal to 0? It's similar to that. It's not exactly the same thing. Whereas this is a way more complicated thing that involves data that's scattered all up around random access memory.
Yeah, it makes sense.
Okay, cool. Yeah, so continuing on here, increasing. Oh wait, so I already kind of skimmed through here. I did actually find most of this section pretty obvious. We did get some more of the struct freezing stuff. The author talks about some problems you could run into if and they're usually not challenges I worry about, and I don't use freeze as much as the author does. But I guess I'll just skim through here. There was one part that I thought was interesting that I took note of. Let's see. Okay, so something I took a note of is that if I find myself needing to freeze all this stuff, I usually wind up also being in a situation where, the calling code, so I'll do something like this because I don't want to mess up data that I received from the calling code, but I don't usually do something like this to try to perform defensive programming on behalf of the calling code. I don't know how to explain that, but like I tend to do something like this, line items.dupe, in order to not break the calling code, but I don't do line items.dupe.freeze in order to prevent other calling code from breaking my line items. It's just not something I usually do. I could do it, and maybe I should do it as a form of defensive programming. It's just not something I tend to do the way the author is doing here. It is important to know about it, though, and maybe I should make use of it at least occasionally as a form of defensive programming. But yeah, I rarely personally write code like this with the freezes, and I will dupe this if I received it from elsewhere and I need to mutate it. So I feel like it's my responsibility to handle the data I receive with care, but it's not my responsibility to take on that responsibility from other parts of the code written by other people. It's just like the way I generally wind up dealing with programming in Ruby.
Miles, do you know if dupe does an immediate duplication, or is it copy on write?
So based on what we read in the last book, it seems like it would be copy on write, actually. But I don't know for sure. If you made me take a guess on a test, I would guess that it does copy on write. I don't know if you remember, and I don't fully understand why, but there was something that it mentioned in the other book that there's a Unix optimization around copy on write that can allow